In this video, I'm going to show you another monoid that's quite important, which is the monoid of functions that input and output the same type, with function composition as the monoid operation. So the first thing I'm going to show you is an operator called function composition, which takes two functions and applies them one after the other. This is written as a dot, and its type looks like this. So there are two different viewpoints on what this thing does. You can either see it as taking two inputs, namely a function from B to C and a function from A to B, and it outputs a function from A to C, namely the function that first applies this function and then applies this function. But you can also equivalently see it as taking three inputs, a function from B to C, a function from A to B, and a value of A, and outputs a value of C. So these two viewpoints are equivalent, and the reason that this operator is a bit hard to understand is that you need to be able to shift between these two viewpoints. So to define it, I need to use the second viewpoint. So I'm going to write compose g f x equals g of f of x. So I call first f, and then I call g on the result. It may be a bit confusing that this looks like it's written backwards. Why is this B to C and then A to B and not the other way around? This is a bit of a historical accident. It's so that it agrees with the fact that when we call a function, we write the function name first, and then on the right-hand side of it, we write the inputs to the function rather than on the left. So I get confused by this all the time. So personally, the way I deal with this is that I pronounce this operator as after. G dot f, I pronounce this as G after f. Okay, so this operator is quite useful in functional programming because it's useful together in conjunction with functions like map and filter, which take a function as one of their inputs. So what we're going to do is we're going to make a monoid with function composition operator as its operation. So we can do this for functions that have the same input and output type. So I can say composition is a monoid on functions from A to A. And I can say define composition equals make monoid. Now the neutral element, I'm going to leave as a blank for now and come back to this later. And then for the operation, I'm going to have dot. I'm going to put this in a comment because this won't compile yet. Before talking about the neutral element of this monoid, let's make a start on one of the equations that we need to prove to know that this thing is a monoid, which is prove that h after g after f is equal to h after g after f. So this is the rebracketing equation for this monoid. So this is now an equation between two functions. So there is a very interesting question of what does it even mean for two functions to be equal? And this is worth thinking about a bit. It's actually quite a complicated question. And there are several different answers that are reasonable. So the most strict thing that you could say for what does it mean for two functions to be equal is that they are literally the same procedure in memory. So they live at the same memory address. Or you could weaken it a little bit and say that they're allowed to live at different memory addresses, but they must consist of the same sequence of machine language instructions. Or you could weaken it a bit more and say that they're allowed to be more different, but they must have something like the same runtime behavior, like taking the same amount of time. The weakest reasonable thing that you could say is just that they send equal inputs to equal outputs. And that last one is the one that we're going to use. So for our purpose, we're going to consider two functions to be equal if they always return equal outputs for the same inputs. So for example, that means that we can consider a slow function to be equal to a fast function, as long as they have the same input output behavior. So back to our proof of the rebracketing equation. So it turns out that it's not actually currently possible to prove this in ask, but we can do the next best thing. We can prove that if we call these two functions on the same input, then the outputs will be equal. And in fact, I can prove this in one line using tested. So the reason this works is that when ask runs each side of this equation, they both give h of g of f of x, like this. Okay, so let's come back now to the question that I put off earlier, which is what is the neutral element for this monoid? So what is the function for which composing with it is the same as doing nothing? The answer is the identity function, which is the function from a to a, which just returns its output. So define id x equals x. So this is going to be the neutral element of our monoid. So I can now complete this definition, define composition equals make monoid id dot. So now I have two more things that I need to prove. I need to prove that this really is the neutral element. So I have to prove that id after f is equal to f, and I need to prove that f after id is equal to f. So again, just like before, I can't actually currently prove these in ask, but I can do the next best thing, which is to prove that if I call both sides with the same input, then I get equal outputs. And in fact, just as before, both of these go through in one line by tested. There we go. You can also think a little bit about what would happen if you use reduce with this monoid. If I don't have reduce in scope right now, but it would take a list of functions from A to A, and it would collapse them all into a single function from A to A by sequencing them all one after the other. So you can use this to sequence a pipeline of operations.